This next section is lateral analysis of steel buildings, generally for wind loads. We're going to talk about some of the practical considerations in designing lateral load resisting frames for wind. We're going to talk about some general things that apply to modeling and loads and so on. We're going to talk about the various limit states, serviceability, strength, and stability, stability limit state under factored gravity loads. And we're going to talk about some analysis parameters that we use in our practice that you may be interested in sharing the experience. Some general issues. It's important first to identify the vertical lateral load resisting system. And I'm going to abbreviate that throughout this lecture as the VLLR. So when I say VLLR, that means the vertical lateral load resisting system. For any of you that have worked with architects, you know that if you're going to get the distribution of lateral load resistance the way you want it, you better get to them early. And it always is a negotiation. No, you can't have a brace frame here. Yes, you can. No, you can't have a shear wall here. Yes, you can. If you move it over one bay, I'll give it to you. If you don't, I won't. It's a negotiation process. And the important thing we try to teach our engineers is get there early, because the earlier you get there with him, the better you are in getting what you want. And what we're after here is getting a lateral load resisting system that's fairly symmetric in plan, so that the center of resistance or the center of rigidity of the lateral load system is pretty close to the center of pressure of the wind load that's applied to the building, and also close to the center of mass of the building. If you got the center of resistance over here and the center of mass over here, what are you going to do? You're going to put a big torque on the building, and that's undesirable from a seismic standpoint. In earthquakes, it's certainly undesirable from a wind standpoint, because it may cause your building to just go into a torsional oscillation. So proper location of the lateral load resisting system early in the project is a key element to a successful design. You have to decide what you're going to model. Are you going to model the whole building, including the gravity loaded columns and the lateral load columns? Are you only going to model the 2D frames? How are you going to do that? That's a decision that you as the engineer need to make early in the process. With today's software, it's becoming more and more easier and easier to just model all the columns and all the beams. Why? Because it gets you the proper distribution of gravity loads in the building spatially, and it also ensures that you capture the P delta effect of the gravity loaded columns properly in your design. We're going to talk more about that P delta effect in a moment. But you have to decide how much of the building you're going to model in your lateral load system. If you're not going to model anything but the lateral load frame itself, then you've got to be sure that the gravity loads that are on the building are properly accounted for in the leaning column effect, or the P delta effect, in your moment frame. So that means you've got to add, if you're only going to model the moment frame, you may have to put a dummy column in there that has all that gravity load from the rest of the floor that's tributary to that lateral load system, to be sure you properly model the P delta effect. The P delta effect can weaken a frame by 10 to 15%, so not including that gravity load in your lateral load model can cause significant errors in your drift and in potential sizing of your members. So that's the decision you've got to make, and different projects have different complexity, and you may make that decision differently. I'm here to tell you that with this software, many of our engineers say, yeah, just model the whole building. They actually can set it up and put it all in there just about as fast as they can, doing a gravity analysis by hand off to the side, and then transferring all of that information over to the lateral load resisting system that they model. So you've got some flexibility there. I always really encourage the young engineers to get a feel for the problem. And, you know, I think many of our young engineers are guilty of just immediately running off to the computer program and setting up the model and putting in the loads, and then out come the results, and then slap it all in the drawings without looking at how reasonable the answers are, and does the building make sense? Is the frame moving the way I think it should move? I think it's very important when you do a computer model to just put the wind loads on there and see if the frame deflects in a logical way. It's a good way to debug the model as well, to see if it's behaving intuitively like you think it should. These are some of the things that I think we as engineers need to do to be sure that our computer programs are giving us the answers that we think they are, and it's not the garbage in, garbage out problem. When frames are drift controlled, and as I said earlier, I found all steel moment frames are almost always controlled by wind drift or seismic drift. You may want to do an optimization routine, and some computer programs have the ability to tell you how much deflection you're getting from column shear, beam flexure, and so on, so you know where to put the material to get the extra drift control that you're looking for. The other way to do it is the old way, by trial and error. Just increase the beam and increase the column and get the drift till you get what you want. That may not be the most optimum way to do it, and there are optimum routines out there in some of the software that do that for you. Remember to check foundation load for net uplift under braced frames. I've always found that braced frames are always desirable over moment frames in wind climates and even in low and moderate seismic zones, because you're going to design those for strength, and your drift control, you get it for free. When you do moment frames, you design for drift and you get the strength for free. It's the other way around. So you're going to end up with a lighter steel building if you use brace frames than you will if you use moment frames. So remember that. Brace frames are generally the frame of choice. The problem is architects don't like them because they take up space. So you got to negotiate with them where you can have them. And you want to have them uniformly distributed over the plan. Another good system is to combine brace frames with moment frames, so you get this synergistic effect where the brace frame helps the moment frame as you go up and down the building. That's a good system to use. And it's particularly good for a seismic zone, because that moment frame then can be your so-called backup system toward the tail end of the earthquake. When the brace frame connections have maybe buckled or failed, you got that ductile moment frame that's giving you that post-earthquake resistance that you like to have. So these are just some of the issues, general issues you got to think about. In our practice, we look at 3 different limit states when we think about designing a lateral load resisting system for wind load. We look at a serviceability condition, a strength condition, and a stability condition. And we actually number these: analysis 1, analysis 2, and analysis 3. Now, serviceability means service loads. That's checking drift. And if your building is tall and slender, you check it for perception to motion. That is the guy on the top floor going to get seasick? If you have a 60-story building in Chicago on the lakefront, perception to motion might be the controlling factor if it's an all-steel building. More controlling than drift, more controlling than the load combinations for strength. So serviceability is an issue that you always have to be mindful of. Strength, of course, is code-specified load combinations that we have to design for. For wind, it's 1.6 times the nominal wind load is specified in the building code. And obviously, you have to consider P delta effects in your strength analysis model. Stability is another one that some engineers have a hard time getting their arms around, but it's basically stability of the building under sustained gravity loads. And I'm going to show you situations where most of the time that's not going to control, but there are some conditions in certain types of buildings where you've got to pay attention to that. Okay, I mentioned we number these: analysis 1, 2, and 3. I want to introduce you right now, and we'll talk about this more in a few minutes, but I want to introduce you to the concept of the interstory stability index, Q. You have a multi-story building, anywhere from 2, 3 levels all the way up to 60 or more levels. Every story has a Q value, a story stability index. And that story stability index is actually identified, for those of you that design concrete buildings. Shouldn't talk concrete in here, but for those of you that use that other material, the ACI 318 code actually in Chapter 10 uses the term Q for the stability index. It's also a term that's used in the literature a lot. Stability index Q. What is it? It's P, the load on the story, the sum of all the gravity load on the story P, times delta, the story drift of that story relative to the story below, divided by V, the shear, the story shear on that level, divided by H, the story height. That is what's called the stability index, and it's a good measure of the stability or the lateral load resistance of that floor. We're going to talk about more of that later. Some of the analysis parameters that we have to worry about in our model. Well, we got to think about how big is the lateral load? Where do I get that? How big does it need to be? How do I apply it? Building mass is important when you're considering the P delta effect. P is the vertical load. P means mass. You've got to get the mass part in there. Member stiffness. What am I going to use for my EI of my members? Beam column joints. How am I going to model the beam column joints? Everybody's heard of panel zone deformation in a moment frame. Real high shears in the beam column joint, and that very high shear in that beam column joint actually causes additional shear strains in the joint that adds to the drift, the story drift at that level. How am I going to account for that in my design? We're going to talk about that in a minute. Diaphragm modeling and braced beam. When I say braced beam, I'm talking about the beam that's part of a chevron bracing system or an X-brace system. Some real gotchas out there that we're going to talk about when you design brace beams. Foundation flexibility. Many engineers take the easy way out and say, I'm going to assume the base of my foundation is pinned. A simple assumption, rarely true, very conservative. Every foundation has a certain amount of rotational resistance at its base, whether it's sitting on a spread footing or whether it's sitting on a pier. Whatever it's sitting on, it's got some rotational stiffness. And the reason you should count on that is because if drift controls the design of your building, the worst drift condition you'll have is probably in that first story. Why? Because it's usually a taller story. And if you take that tall story as pinned at the base, you're going to put a lot of extra steel in those beams and columns in that first story to keep that story drift under control. So one way to mitigate that problem is to count on the actual stiffness that's there at the foundation when you do your computer model. Don't be afraid of doing that, because there's a simple way to do it that I'm going to show you here in a second. We also have to say, okay, for all of these serviceability limit states, strength limit states, and stability limit states, what's the acceptance criteria? What's my fail, pass, fail, go, no-go requirement? We're going to talk about that. Okay, serviceability means usually drift or perception to motion. For drift, different engineers do different things when they check drift. Some engineers use the nominal code load, which is usually the 50-year mean recurrence interval windstorm, or for an important building with an I factor of 1.15, it's a 100-year storm. Some engineers say, I'm going to check drift for that storm. Well, I found that I think that's pretty conservative, and many of the wind tunnel guys that do perception to motion checks for acceleration in tall buildings, they usually use a 10-year storm as a more realistic storm, or a 5-year storm. And so what we do in our practice, we use a 10-year storm to check drift. And we say, okay, under a 10-year storm, we're not going to let the story drift be more than L over 400. The story height divided by 400. Some engineers say, hey, that's not conservative enough for me. I want to do L over 400 for a 50-year storm. Guess what? There's no code requirement here. It's a serviceability issue. It's not a life safety issue. You can do whatever you want to. So what we really do in our practice for hospitals and institutional buildings, we use the nominal wind load, that is the code specified wind load, the 50 or the 100-year load for institutional buildings. And for developer commercial kind of buildings, we use the 10-year storm. That's just the way we do it. You can do whatever you want. For strength, the code tells us what we have to do. It says you're going to design this building for a 50-year mean recurrence interval storm. or you're going to design it for the 500-year earthquake. It tells you what you have to do for strength, because that's life safety. For stability, the code doesn't even really talk about that directly. There are some inferences to it that we're going to talk about. But to check stability, it's more of a stiffness issue. So you can use any lateral load you want to in checking that stiffness, and we'll talk about that more in a second. How do I get the 10-year storm? If I'm going to use a 10-year storm or a 5-year storm or a 75-year storm, how do I get that? Well, guess what? ASCE 7, Chapter 6 in the commentary has a little table. It shows you how to convert from a 50-year event, which is what's mapped, to a 10-year event or a 25-year event or whatever event you want. In the case of a hurricane zone along the coast, the mapped velocity is 50 years, and if you want a 10-year velocity, you take that velocity multiplied by 0.74. If you want the load, it's 0.55 of the load. That is 0.74 squared is 0.55. So from a load effect, it's the square, it's 0.55. For the non-hurricane zone, it's a different multiplier. But anyway, you can get these recurrence interval values in a table in the commentary to ASCE 7, Chapter 6. Chapter 6 in ASCE 7 also has a requirement for wind load combinations or wind load cases that you are required to check. Here they are, as shown in Figure 6.9. You're required to put the full wind load on the projected area of the building in two orthogonal directions, usually the principal axis directions, in the x direction and in the y direction, either direction. Either direction in the x, either direction in the y. And that's basically what's stated in Case 1. Case 2 is the same thing, only we're going to make you put, because we know the wind load doesn't just blow uniformly across the width of a building, even in a symmetric building in an open country environment, the turbulence in the wind produces a non-uniform loading effect that causes a potential torsion on the building. So ASCE 7 says we're going to give you a 25% reduction in the base shear, but in return for that, we're going to make you put a 15% eccentricity to your wind load to account for this torsional effect. That's load case 2. Load case 3 covers the case of a diagonal wind, because we know the wind isn't always just going to blow on the orthogonal principal axis. You could get a quartering wind that might control a corner column or might control some other part of the lateral load frame. We say you're going to apply the load simultaneously in two orthogonal directions at 3/4 of the value, and that's the same as kind of putting a diagonal wind load on there. So that's case 3. Case 4, the final case, is we're going to put that diagonal wind on there like case 3, but we're going to say, hey, that diagonal wind might also have an eccentric effect due to the turbulence in the wind. So we're going to give you some reductions there, but you got to put that same 15% eccentricity about each principal axis independently. But now we're going to take another reduction on the base shear in each direction that you get to apply. These two torsional cases, 2 and 4, discourage an engineer from putting all the lateral load resistance in his building into the center of the building and end up with a building that has very low torsional stiffness. If you try to do that in design for load cases 2 and 4, you're going to put a real torque on your building that will increase the base shear on the lateral load frames that are close to the center of the building. And it'll quickly discourage you from doing that, which is what the intent was. Okay, stability under gravity load, that analysis 3. We're going to get into this more, but for right now, let me just tell you, when you check that load case, we're going to make it real easy, and we're going to put 100 kip force at the top of the building in the x direction. Independently, as a separate load case, we're going to put 100 kip force at the top of the building in the y direction. And then independently, we're going to put 100 kip-inch torque on the building as a torsional moment. And we're also going to do that at the top of the building. I'm going to do it at the top of the building only because that's going to make it real easy to check the torsional stiffness or the translational stiffness as each floor. Why? Because the story shear is the same at every floor. So that makes this check real easy to make. Let's talk about torsional stability, because some engineers aren't used to this concept and don't understand why it's important. We all know what translational stiffness is, right? You apply a load and you have a certain stiffness in the frame that produces a certain deflection under that applied load. Torsional stability is a function of the mass on the building or the floor or the frame at that level. And the translational stability is a function of the mass and the translational stiffness of the story. That is, how much does that story deflect under a uniform shear? Well, torsional stability is, instead of being mass, it's mass moment of inertia, which we'll talk about in a second. And then instead of translational stiffness, it's torsional stiffness, inch kips per radian of twist. So it's the same thing as translational stiffness, except it's in a rotational form. When is torsional stability an issue? It's an issue for heavy buildings with a high mass moment of inertia in which the lateral load resisting elements are located near the center of the mass, as opposed to being located far out around the perimeter. There have been many buildings during earthquakes that have suffered severe damage due to a torsional instability in the building, because the structural engineer put all the lateral load resistance in the core and put nothing around the perimeter. The earthquake came and it got the building rotating in a torsional manner and created a little bit of a torsional instability that overloaded the frame and caused failure or damage. Torsional instability is a bigger problem for seismic perhaps than it is wind. That's when you see the damages during earthquakes. So the seismic provisions have what they call torsional irregularities that they make you design for and check. We also have a similar problem in a wind condition. We don't want our buildings under wind load to be doing a torsional oscillation. You generally want torsion to be the third mode. You want the first mode to be a translational mode in one direction, the second mode of the building to be translational in the other direction. The third mode is the one you want to be torsion, not the first mode or the second mode. If you design a building and the first mode of vibration is a torsional mode, you probably have a torsionally flexible building that you should stiffen in torsion. It's a good check. When you're doing a computer model, it's real easy now to check your mode shapes, right? You just push a button and you can see these mode shapes come out. Watch the building dance. If the first mode is a torsional mode, you need to go back to the drawing board and modify your lateral load resisting frame so that the torsional mode is the third mode, not the second mode or the first mode. It's a very good, simple rule of thumb. Anyway, back to mass moment of inertia. Mass moment of inertia is one of the players in torsional instability. And if you have a small footprint with all your lateral load resistance in the center, you're probably going to have a small mass moment of inertia. If you got a big floor and you got your mass distributed out over a wide area, you're going to have a large mass moment of inertia. The mass moment of inertia expression is simply the mass of the floor divided by the area of floor times Ix plus Iy, where Ix is the area moment of inertia about the x-axis and Iy is the area moment of inertia about the y-axis. That's simply what mass moment of inertia is. Now, here's good and bad examples of torsional requirements. Poor torsional behavior will be the one on the top, where all the torsional resistance is in the middle. Good torsional behavior is when you put some of that lateral load resistance on the perimeter of the building and distribute it around the building, not all in the middle. You want the bottom two cases, not the top two cases. Earthquake damage has indicated that people that design buildings like the top two cases, you're going to get a lot of torsional rotation during the earthquake and probably a lot of damage. So you want to end up with good distribution of lateral load resistance. Again, if that torsional mode is the first mode, you are probably, that first two cases, not those bottom two cases. With that, Steve's back there telling me he's hungry. Oh, I got one more, okay. Okay, well, you're pretty on top of this. Analysis 1, I mentioned we number our analysis 1, 2, and 3. Analysis 1 is serviceability. What mass do you use for these different load cases or these different analyses that we do? Well, you want to use the sustained building weight for serviceability and your best estimate of the actual self-weight of the building for that check. For analysis 2 strength, the code tells us what to use. You use the ASCE 7 load factors, either ASD or LRFD, depending on your persuasion, which method you like. The code tells you what load factors. Analysis 3 stability, you use the same load factors as you design the column without wind loads. That is 1.2 dead plus 1.6 live. That's the load factor we're going to use for mass in our building mass when we're getting around to checking our P delta. And remember, this P delta phenomenon is very important when you're doing your lateral load analysis. With that, good place to stop. We're going to go eat, and everybody's on their own, I understand, and we're back at 1 o'clock.